Let's have another go at this specific heat capacity experiment. And this time I'm going to put some steel nuts into the water and see if we can measure the specific heat capacity of steel. I made sure that the nuts were completely submerged so that way you get maximum heat transfer between them and the water. You want them both to be in thermal equilibrium with each other. Okay, away we go. Okay, let's have a look at these numbers again. This did not go well, but let's go through what we've got. These are the masses of steel and water we had in our experiments. This is the power that we found in the previous video. This is the power output of our candle. It ran for 22 minutes 38 seconds, which is 1,282 seconds. And we have this combined mixture of water and steel in a single container. The combined mass is this. The overall heat capacity of this object we don't know because it's a mix of two materials. But I'm not going to go through this equation, but I show it in one of the files on my site. If you have a mix of two materials, say water and steel, you can find the overall heat capacity of their mixture by just doing the mass of water times the heat capacity of water plus the mass of steel times the heat capacity of steel. And that gives you, that equals MC, the total mass of the two materials times the heat capacity of this entire object. And so I rearranged, and remember we know the mass of the water, the heat capacity of water, the mass of steel. And this thing, MC, we can actually find by taking the old heat capacity equation and rearranging it, E equals MC delta T. MC is just E, the energy you put in, divided by delta T, the change in temperature. And we know the energy we put in because it's just the power of the candle times the time that it was on, or lit. And then we divide by delta T, and this comes out to 470 joules per Kelvin. So we have to put in 470 joules into our water and steel nut mix to increase its temperature by 1 Kelvin, or 1 centigrade. So we have all the numbers we need, and I substituted them all in, and it comes out with a heat capacity of steel for 1.93 joules per gram Kelvin, which is, or 1,900 joules per kilogram per Kelvin, which is not correct. It's not even close. It should be 420 joules per kilogram per Kelvin. So my answer is overestimating it by a factor of about 5. And I guess a good thing to ask is why? I think there are a lot of sources of error in this experiment, and I might actually make a follow-up video trying to fix a couple of them. The most obvious one that I can think of right away is the fact that the candle was more run down in this run of the experiment than in the other video, so it may have had a very different power output. So I might try and have a go at this a second time and iron out some of the inconsistencies. I'd be happy if I could get to within maybe 50% of the correct value, but a factor of 4 is just no good at all.